it says the flame of a candle is 30 centimeters above a table. A 10 centimeter tall glue stick container is standing 35 centimeters from the candle. How long is the shadow of the glue stick? The flame of a candle is 30 centimeters above a table. I think I just read this. Okay, I just read it already, so I'll get into it. So, all right, so what we got going on here is we have a, I'll just say a candle is just like a stick like that, right? It's 30 centimeters above a table, so this would be 30 centimeters. We make our table. And a 10 centimeter tall glue stick is sitting there, right? So 10 centimeter long glue stick. And it's standing 35 centimeters, so this would be 35 centimeters between each other, right? So from like there to there. And it says, how long is the shadow of the glue stick? So what you could do here is say, okay, well, if this is our candle, right, like our flame up here, then it would shine down there, and the shadow would be really that length, right? The length from the glue stick to where the light actually hits the floor again. So that's what we're looking for here. You guys have any ideas on how we could?
We're gonna have to find the total length of like if you look at like the entire big triangle, we have to find the entire length, then we can subtract 35 to find that x.
Okay. See what you're saying? Yep.
We have, because we need to find the little green arrow from the glue stick to the floor, right? Or no, that's what we're looking for is x. Oh yeah, so we need to find something else first.
So here's what we're gonna do is we've actually got two triangles going on here. So you can think about this one as being one of our triangles, but we could also think about the big one as being one of our triangles, right? And these are actually similar triangles, right? They actually have all the same angles, so they're just like an enlargement of each other, right? But the angles be the same. So here's what we do: we just actually compare the two triangles. So let's actually just look at the small triangle first, here, right? Make that red, so that's good. And I could call that either way. I could call it x over 10, or I could have went 10 over x. It actually wouldn't matter which way you did it. But I'm just like setting up a ratio here, because the ratio of this side length to this side length should be the same as the ratio to this side length to this side length, like the whole thing, right? But now there's an x involved, so we got to do a little bit of algebra. So anyway, so x over 10, right? So this one to this one, so x over 10 is equal to, what would the top of the next expression be?
35 plus x.
35 plus x, good. Right, over 30. And there, now we're just dealing with a little bit of algebra, right? You guys okay with what they just did there? Okay. All right, so bringing it up, we'd have 30x, right? Just bringing this one up is equal to 10 times 35 plus x. So I'll distribute that one in, so we get 30x is equal to 350 plus 10x. I'm going to bring 10x to the other side, so we're going to have minus 10x minus 10x, so we get 20x is equal to 350. So you end up getting, 17.5 centimeters. Okay, so that's one style of question that you guys could get. Yeah, you know what? For the sake of time here, I'm gonna maybe come back to 2 if we have time, because number 2 will be similar to that first one, and there's actually an example of this one in the notes above too. So, but it'll be similar. So I sort of really want to make sure I get to these ones in time. Okay, so Olaf Romer noticed that the time when one of Jupiter's moons was eclipsed by the planet changed depending on the season in which the measurement was taken. When the Earth was closest to Jupiter, compared to when the Earth was furthest away from Jupiter, so on the other side of the Sun, there was a 1,320-second difference. Romer correctly interpreted this observation to be the effect of the increased distance that light had to travel to reach the Earth. If the Earth's mean radius of orbit is that, what is the speed of light that Romer measured? All right. So what's going on here, right? We've really just got to figure out the difference between actually they even told us the difference, right? So if we're gonna figure out, so in the one case it was this, it was the time took to get to this one, right? But then the other, when I'm on the other side of the planet, it would have been from here all the way to there, right? So really what we're doing is we're just using v is equal to d over t to figure out, so there's a certain difference in time, right? This is the idea. The difference in time between these two, right, would be what we're going to use here. And then it's just simply this. It's just v is equal to d over t. And we know the mean radius, right? Because the mean radius, right, of the planet would be that thing. So just careful on this one, right? Because the mean radius would be from the center of the sun to the center of our planet. Multiplied by 2, right? I actually need the diameter of this circle. So we need to go, the velocity would be equal to 2 times, yeah, 1.5 times 10 to the 11 meters, right? The mean radius, or orbit, divided by, and then it actually gave us the difference between the times, right? So that's just 1,320 seconds. So that would be equal to 2.27 times 10 to the 8 meters per second, which is pretty close, right? Because do you guys know what the speed of light is? Like the accepted speed of light now? Yeah, 3, right? So that's definitely in the right ballpark, right? Like that was actually pretty good first estimation there. All right, now. So the Michelson-like apparatus diagram below, the observer found that in order to observe the return light ray, the mirror had to rotate at 707.1 hertz. What is the speed of light calculated from this experiment? All right, so remember what's happening here, right? So this is the observer over here, and we got the light source. And what's happening is that the light, right, would shine this way, bounce off this edge, travel all the way down, 35 kilometers, and then all the way back. So how many kilometers in total? 7, right? So go there and back. That's a big place to make a mistake here. And then bounce up the mirror and come back up again. And what's happening, right, is he's going to adjust this knob. He's going to make this thing turn at a different frequency, right? Different speed going around. So he's going to keep on fiddling with this until it's going the perfect speed, so that one chunk of this thing, right? 1/6 of a turn in this case. There's 6 sides in this one. So 1/6 of a turn would be exactly the amount of time that it took for the light to go down and back. So really, we got to figure out. Well, they actually.
Would that be how like old movies worked? And if they shine a light on a picture and spin it really fast, would it make it look like it's moving or something like that?
I don't know. Maybe.
Because
not exactly
you've
sure.
seen like old movie picture, whatever, when they spin and they shine a light into it, it shows like a moving picture or whatever. So I don't know how it works.
Maybe. Yeah, we can look into that.
I just thought about it. Well, they didn't exactly have Blu-ray back then.
Yeah. Okay. So guys, what we got to do? So we got to calculate really. So they gave us the frequency of this. They said the frequency was equal to 707.1 hertz, right? So do you guys remember what frequency is? Frequency is number. Yeah, but what is it actually saying? It's saying that this thing is going around.
It's probably
That many times in 1 second.
Yeah, it's going around 707.1 times every second, right? Like that's fast, right? This thing's cruising. I'm less interested here in this case in the amount of times that goes around every second. It'll be a lot more valuable to me for me to figure out how many seconds does it take to go around once. Right? That'll get me a little bit closer. So let's do that. So let's figure out the period for this thing. So t is equal to 1 over frequency. So t is equal to 1 over 707.1 hertz. So t is equal to 1.414 times 10 to the negative 3 seconds. So that would be good, right? Like we could use that if we wanted to, right? But we actually don't want the speed for the whole thing, right? I actually just want one-sixth of that speed, don't I, right? Because I just want this thing just to turn once, right? Because that's going to be the amount of time that we
just divide by 6.
we just divide by 6, right? We have to figure out 1/6 of this thing. So step number 2 is we're going to say, okay, the change in time, or the time here, is going to be 1/6, or 1/6 of the period. So that'll be, change in time is 1/6 times our number down there, 1.414 times 10 to the negative 3 seconds. And so that ends up being 2.357 times 10 to the negative 4 seconds. Okay, and we're almost done, because now, that's the good thing about this unit, is light travels at a constant speed. So we get to use the easy formula, right? We get to use V is equal to d over t. So if I want to figure out the speed here, we'll say V is equal to, like I said, this is a point where people might make a mistake, right? So how far did it go? 70, right? Because it was 35 that way, and it was 35 back.
But would we need to account for the fact that from the light source to the meter then? From
No, this is gonna be so negligible here, right? Like you could be like right beside it, and the whole
If
thing
you
would
actually
work.
think about it, like they're like this close together, and then it's going 35 kilometers that way. That's like
Yeah, we're talking about like centimeters here, and we're talking about kilometers here. So the error is like it's negligible difference
and then
here.
wouldn't you need to use trigonometry to find the distance?
No, and I know what you're talking about. So like it's because this looks like a triangle. Again, that triangle is negligible, right? The length of this one would be pretty much the same, like identical as the length of that one, right? We don't have to try to figure out, or actually, sorry, the length of this one would be identical to the distance from the middle of this to that one, right? Because the triangle that we're dealing with is so small. It's just the width of this mirror, like from there to there, right? So no, we can treat it like it's just straight there and straight back, right? We don't have to, I drew it like a triangle just so we can see it, but yeah, it's for all intents and purposes it goes straight down there and then straight back.
Do we need to change kilometers to meters?
We do have to change kilometers to meters, though. Yeah. So we've got, so you could say it was 2 right there and back times 35. Let's change that into kilometers or into meters first. So let's say, let's just do 70. All right, so 70 kilometers. How many meters is that?
70,000.
Yeah, so 70,000 meters. So we'll just say 70,000 meters divided by the time we figured out. So 2.357 times 10 to the negative 4 seconds. So we get a speed of 2.97 times 10 to the 8 meters per second. And that is close, right? That's actually getting really close because it's like 2.99. You know, so like we're really in the right ballpark here. Okay, so since we have time, let's go back to number 2. So sorry for the jumping around. All right, number 2. A pinhole camera is a device that consists of a light-proof box with a pinhole punched into one end and a screen of some sort or some kind on the other. An image is formed on the screen from light traveling in straight lines from the object through the pinhole. What's the size of the image of a person that is 1.9 meters tall and is standing 7.5 meters from a pinhole camera that is 25 centimeters long? I really recommend in these ones drawing a picture first, right? Kind of figure out what it is we're actually dealing with. So let's draw our pinhole camera. So our pinhole camera is 0.25 meters long. So from there to there. Our person is standing over here, right? So we got maybe like person. Okay. And from here to here is going to be 7.5 meters. And now the way this works is there is a pinhole. There's a pinhole right in the center of this thing, right? So what would happen, you could think about the light from the top of this person's head, right? Like, so the sun is shining on us, and all of me is actually shining light over toward this camera. But for our purposes, we're just going to consider the light on the top of my head and the bottom of my foot, right? Because that's going to be the very top of me and the very bottom of me. And I'm not going to care about the middle stuff, right? Because I just want to figure out how tall this thing's going to be in the middle. So what's going to happen here is if I draw a straight line from the top of my head down through here, right down through the pinhole, then the top of my head would actually end up shining down there on the other side in there, right? If the pinhole is right there. And then my foot would do the same thing, but it would shine, you know, through here, straight lines again, and go back up, and now my foot is up there, right? So you guys see what would happen with my image on the other side of this thing? Yeah, it'd be an upside down image, right? So a pinhole camera, these are like ancient cameras. They did this like thousands of years ago, right? They figured this one out. And it does just make an image of the person, but it makes it an image of the person inverted. So it'd be, you know, my head, arms, and legs in there, right? So now this one really isn't too bad. It's actually even a little easier because now it's asking for what's the size of the image, so that'd be my x, right? These are similar triangles, right? So this triangle I got going on over here, right? It's not a right angle triangle, but that doesn't matter. This triangle, well, the big one, is similar to this triangle, the smaller one. So the sides, right, we can set up ratios of these things. So I can say, okay, x over, right, the length of this one was that, so just say x over 0.25 meters is equal to, and then, oh, I didn't write my height of my person here. His height was 1.9 meters, right? So then just make sure you get the x has to be with that one, right? They're the two that are similar, or the ones that are on the same side. So that's going to be 1.9 meters over 7.5 meters. I think you guys can do this one. But anyway, in the end, you get 0.063 meters, which would also be equal to 6.3 centimeters.